Fellow researchers and students, we will discuss this time hypothesis testing and statistical inference. Our topic is making inference from the sample to the population. Hence, we shall define sample and population and what qualifies a sample for inference. A population is a complete set of participants, subjects, or objects. A sample is a portion of the population. A parameter is the descriptor of the population. A statistic is the descriptor of the sample. Measures of centrality, dispersion, and location are examples of statistical descriptors. A non-probability sample is a sample selected on the basis of subjective judgment by the sampler. A probability sample is a sample selected randomly, the size of which has been computed on the basis of statistically accepted criteria. It is the sample that qualifies for statistical inference and hypothesis testing. Sample arithmetic mean, sample median, sample mode, sample standard deviation, sample variance, sample range, sample correlation, and sample difference are examples of statistics. The plural of the word is statistic. Population arithmetic mean, population median, population mode, population standard deviation, population variance, population range, population correlation, and population difference are examples of parameters. Statistical inference is the process of using statistic data from a sample process to describe the sample, to estimate or describe or make conclusions about the characteristics of the population, and requires an appropriate sample. An appropriate sample must have a size computed on the basis of acceptable statistics, confidence level, and margin of error. It must also be randomly selected. It is likewise called a probability sample. Hypothesis testing is the process or the part of process of statistical inference. It commonly involves testing of significance. A significant result means that the statistic or descriptor of the sample would more likely be a descriptor of the population represented. A result that is not significant means that while the statistic is observed in the sample, more likely it would be zero in or would not be observed in the population. These are the types of probability sampling. One is simple random sampling. Next is stratified random sampling, which could be disproportionate or proportionate. Third is cluster random sampling. And fourth is systematic or serial random sampling. These are the steps involved in simple random sampling and stratified random sampling. Following are the steps in cluster random sampling. And the following steps are involved in systematic or serial random sampling. We now proceed to the illustration for simple random sampling, starting with sample size calculation. There are two steps involved in random sampling: sample size calculation and sample element selection. In sample size calculation, this is the generally used formula, where small n is the sample size, big N is the population size, and E is the margin of error, assumed to be 0.05 for business studies. We shall program this later in Excel. For the information of everyone, this is the formula that this lecturer has derived from the formula that estimates population proportion, population size known, assuming a confidence level of 95.44%, giving a Z value of 2, a proportion of 0.5, and assuming 1 in n minus 1 is 0 because of a very large n value. We shall now program the former in Excel. May I suggest that you open an Excel sheet and type or encode in the respective Excel cells or boxes these terms and expressions, or rows numbers or column numbers. Once again, you type in the appropriate Excel boxes or cells the following programs, and eventually you will come up with a sample size of 385. Inasmuch as you have programmed the formula for computing the sample size, if you change the value of the population size or the margin of error, the Excel sheet will automatically recompute your sample size. For the sample elements random selection, we have to use analysis toolpath. Again, open an Excel sheet. Click File, click Options, click Add-ins, click Analysis Toolpath. Click Go, check Analysis Toolpath, and click OK. To avoid confusion, open a new Excel sheet and click Data, so that on the right side of your sheet, data analysis will appear. Click Data Analysis, and this box of Program Statistical Tools will appear. Scroll the box, select Sampling, and click OK. So this box will appear. Open a new Excel sheet. Assume population size of 100, sample size of 80. Assume 100 respondents, coded from 1 to 100. Type the codes 1 to 100, starting at A1 and ending at A100. By using sampling in the data analysis, the computer will randomly select any numbers following these steps. Click Data, click Data Analysis, click Sampling, click OK, and this box will appear. Type in input range box A1 colon A100. Type in number of samples 80. Type also random. Click output range, and type D1. Click OK. This will be the output of your computation, giving you 80 randomly selected numbers from 100 numbers. If there are numbers repeated, do the process again with C1 as output range. Hypothesis testing is a process for statistical inference that uses data from a sample to draw conclusions about a parameter or population characteristic. The premise here is that the source of data is a probability sample, not a non-probability sample, and not a population. The steps in hypothesis testing are: number one, statement of the research question. Number two, statement of the hypothesis, the null hypothesis and the alternative hypothesis. Number three is setting the conditions for accepting the null hypothesis and rejecting the alternative hypothesis, or rejecting the null hypothesis and accepting the alternative hypothesis. And finally, testing the hypothesis and making the decision. For the statement of the research question, we can consider two most relevant types of research problems: relationship between an independent variable and a dependent variable, and effectiveness of a treatment, or difference between two or more samples or groups. For the first type, the research question is there a significant relationship between the independent variable and the dependent variable? For the second type, the research question is there a significant difference between the two groups? We shall now proceed to the steps for the first type of research. The research question, is there a significant relationship between the independent variables and the dependent variable, can actually be stated in the following ways. First, of course, is there a significant relationship between the independent variable and the dependent variable? But it can also be stated as, is the magnitude of relationship observed in the sample more likely to be observed in the population? In mathematical form, it is population relationship not equal to 0. On the other hand, the research question, is there a significant difference between the two groups, can be stated in the following ways. First, of course, is the original question, is there a significant difference between the control group result and the experimental group result, or between the pre-test result and the post-test result? Or is the magnitude of difference observed in the sample more likely to be observed in the population? Numerically, the question is population difference not equal to 0? We now proceed to the actual examples of hypothesis testing. On testing significance of relationship, we have the prior information. The magnitude of relationship between price of sugar and demand for sugar, where sample size is negative 0.98896. Is this relationship significant? Assume alpha is equal to 0.05 and the sample is probability. Question: is there a significant relationship between the price of sugar and the demand for sugar? Or is the magnitude of relationship observed in the sample more likely to be observed in the population? Or is the population relationship not equal to zero? The null hypothesis is there is no significant relationship between the price of sugar and the demand for sugar, or the magnitude of relationship observed in the sample would more likely not be observed in the population, or the population correlation is equal to zero. The alternative hypothesis is there is significant relationship between the price of sugar and the demand for sugar, or the magnitude of relationship observed in the sample would more likely be observed in the population, or the population correlation is not equal to zero. If the absolute value of the computed t-value is less than the absolute value of the critical t-value, accept the null hypothesis and reject the alternative hypothesis. If the absolute value of the computed t-value is greater than the absolute value of the critical t, reject the null hypothesis and accept the alternative hypothesis. We therefore need to determine the computed value of t and the critical value of t. And these are the formulae for determining such values. To solve for the value of the computed t using Excel, we go back to the Excel sheet where R has originally been computed. And we shall program the formula for the computed t value. So you just follow the instructions on what to type and on what Excel sheets. And eventually, the computed value of t is solved. It is negative 18.8765. To determine the value of the critical t, we have to divide 0.05 by 2 and determine the degrees of freedom. In an Excel box, say A1, type this command shown on the screen, and the critical t value of 2.306 shall appear. You can also trace the value in a t-distribution table by crossing 8 under degrees of freedom and 0.025 under alpha equals 0.025. The solution is also 2.306. Decision. Since the absolute value of the computed t, which is 18.875, is greater than the absolute value of the critical t, which is 2.306, the null hypothesis is rejected and the alternative hypothesis is accepted. There is a significant relationship between the variables, or the magnitude of relationship observed in the sample would more likely be observed in the population. Inasmuch as the relationship from the sample is significant, it could be applied to the entire population in the findings, conclusions, and recommendations of the study, and not delimited to the sample only. We now go to the testing of significance of difference. For our illustration, let us consider 10 randomly selected students who were given a pretest prior to an intervention and were given a post-test after the intervention. The results are shown in the dataset of the following Excel sheet. Is there a significant difference in the pretest mini-scores and the post-test mini-scores of the students? Question. Is there a significant difference between the means of the pretest scores and the post-test scores? Or is the magnitude of difference observed between the means of the pretest scores and the post-test scores of the two sample groups more likely to be observed in the two groups of populations? Or is the population difference not equal to zero? Our hypotheses are, for the null, there is no significant difference between the means of the pretest scores and the post-test scores, or the magnitude of difference observed in the samples would more likely not be observed in the populations, or the population difference is equal to zero. The alternative hypotheses are there is significant relationship between the two groups, or the magnitude of difference observed between the means of the samples would more likely be observed in the population groups, or the population difference is not equal to zero. If the Excel output P is greater than 0.05, accept the null hypothesis and reject the alternative hypothesis. If the Excel output P is less than or equal to 0.05, reject the null hypothesis and accept the alternative hypothesis. So we have to type once again these programs in the concerned Excel sheets. This is actually the program for determining and comparing the mean scores. There is actually a difference of 3.5 between the two sample groups. Is it significant? In A14, type P equals, then put your pointer or cursor in B14. Click Formulas, More Functions, Statistical, and T-Test. This will appear. In array 1, type B2 colon B11. In array 2, type C2 colon C11. In tails, type 2. In type 1. Click OK. The output shows P is 0.00000012. Our decision will then be, since the probability is less than 0.05, we reject the null hypothesis and accept the alternative hypothesis. There is significant difference between the pretest score and the post-test score, or the observed difference will most likely be observed in the population, or the population difference is not equal to zero. This result indicates that although collected from a sample, the findings, conclusions, and recommendations are good for the entire population. Thank you for viewing, listening, and reading.